Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm here with Kajetan Nürnberger from Infineon and Guy Ben-Haim from Synopsys. Going to talk today about the changes and challenges in microcontrollers in automotive. Kajetan, when we think about a microcontroller, these used to be very simple designs. There was memory built in there. You only got the memory that you had. Things are changing rather dramatically in the MCU world. How does this actually look today, and what did it look like in the past, and what's driving this?
Today everywhere is AI, and now AI is also coming to the microcontroller in the automotive world. In this slide, you can see one example out of the advanced driver systems where you have to process radar to know where the other cars are. Yeah, so one of the challenges you see in the automotive microcontroller is that now everyone talks about AI, and this is now also coming to the microcontroller in the automotive world. On this slide here, you can see one approach out of the advanced driver systems where you definitely need to know where all the other cars are on the road. And this you can do with radar. And then when you get your radar signal, you have to find out in which angle the other cars are. And this is a good approach which you can tackle with a neural network with fast calculation and a precise result of the direction of arrival of the other cars. Obviously, something like this you cannot tackle with the old microcontrollers some years ago, where everyone was still on single core, limited memory. And in the past years, we saw the change dual core or multi-core, like you can see on that slide here. So multi-core is today state of the art, I would say. But when you now talk about neural networks, multi-core alone is probably not enough anymore, especially when you consider the power constraints and also that you are passive cooled in a very hot environment, and therefore you need efficient processing here.
In the past, we kept thinking that when we're dealing with automotive, it's probably going to be almost entirely TPUs or some advanced accelerators or neural network type of chips. Where did MCUs suddenly come into this? They typically were not even thought of in this context in the past.
Yes, but more or less with these hardware accelerators, you always have some limited flexibility, and especially its effort to build such a construct. And now also the market gets more diverse. There are more companies, more players. So to do specific accelerators for specific customers is not really paying off anymore. And therefore, you now have to go to something which you can program by software, which is much more flexible than dedicated hardware accelerators. You still have them if you are really time critical. For example, the timers are still in the microcontroller still, which do some really specific interactions, but especially for the field also of neural networks, for example, where you have a lot of change also during the years. And even now we talk about that software should change during the lifetime of a car, which was not there a few years ago.
Guy, when you look at this, there's a lot more going on here than just the hardware, though, right? I mean, it's the software, it's the design of of this whole system within another system, probably within another system.
That that is right. That is correct. Let me go to show you a diagram. Exactly what you asked. You can see here a system inside a system, or a hardware inside hardware, and also software that runs on top of that. What you see here is a parallel processing unit for DSP processing and a neural network. And you can see different hardware components here that are supported by this DSP, for example, for parallelism of running multiple tasks in parallel. And on top of that, there is a software development kit that helps the software developer develop applications and solutions for automotive. And that is another component that helps the software developer to compile the software, debug the software, simulate the software much in advance before the hardware is ready. Also libraries and automation to create code or binaries to run on top of that hardware. And that is another layer on top of the system inside system that we are talking about here for automotive.
You know, what's interesting here is that you're looking at this from the standpoint of going more mainstream with a lot of this technology. When we first started talking about electrification of cars and autonomous driving and basically ADAS 1 through 5, we started looking at things from very brand specific, company specific types of designs where this is their car, they're going to be doing things differently. What both of you are proposing here is much more of a this is the way you achieve economies of scale and get to market quicker.
Absolutely. The idea of programmable hardware and the tools and the software on top of it that helps the developer to program creates the ability to support many different applications for automotive, starting from neural network and then DSP and then different libraries. And in parallel to that, all the automation and simulation that comes to assist.
In effect, what's happened here is the automakers have finally said, okay, we know what's going to differentiate us. It's really not going to be down at this chip level. It's going to be the way these things are put together, as well as all the other features that we offer, right?
Yes, it's all the features, like you said, not only hardware features to accelerate the application and support it in a hardware level, but also the modularity, the ability to program and use specific libraries for specific tasks. Also, the ability to build everything faster with automation, with different flows, simulations. That is really, really important for the software development side.
Kajetan, how are the automakers looking at these days? When you approach them, say, 5 years ago versus now, what's changed from that side?
What we see from the automakers is that, especially as now the car hardware becomes more uniform, they again specialize, go back to software development. So in the past, we always had the fixed work split more or less, that there was a tier one doing more or less the software after some some specification which was frozen at one state. They gave it to the tier one and they made the software for them. And now OEMs are going back to develop software on their own to more or less differentiate on software level, and also to make the software change more lively, as I said before, so that they also want to update software during the development phase. And I think this also needs new methods to develop software. So we're not talking about anymore going down to the hardware, writing every register on its own, but more or less have some model-based approach where you develop independent for your hardware and have then these layered approaches to get also flexibility and speed in software, because I think it's no secret that on almost every project, software is also the latest state, but normally they are always late. And this is, I think, also a challenge to admit that software is no longer late. And also for us as a microcontroller vendor, it's an important topic that we enable a good software ecosystem.
Guy, this also puts more pressure on the EDA companies, because if they're only going at a high level of abstraction on writing the software, all those other connections need to be done in the hardware side and already built in. You've got to debug that, you've got to plan for all that, and you've got to be able to change it as you need it, right?
Yes, absolutely, absolutely. So in order to deal with that complexity ahead of time, software has to start prior to hardware. I mean, this is a parallel design. You cannot wait for the hardware to be ready until you start testing it. You have to start the software development in advance. Otherwise, you can never meet the target. And based on the complexity, you need to have the tools and automation and simulation that you can simulate the software much before the hardware, much time before the hardware is ready. And for that, you need to have automation to generate or test the software much faster, develop it faster. Here on the screen, you can see one of the models here, for example, in addition to the simulator, there is this Simulink model-based design. So you can start from high-level neural network model and really use automation with a flow to generate a binary that can be executable and optimized for that hardware as an automatic flow. That flow also uses optimizations. So it saves a lot of time for the developer, not needing to do everything manually, start from a high-level model, not only the ease of use, the time savings here, and also the optimization that is done during the flow. If you consider all those aspects, that creates a great benefits to the software developer, and this is how you can do things in parallel, progress with software in parallel to hardware, and get better results in a shorter time.
One of the things that both of you have said, which is really intriguing, is that the automakers for a while said, "Oh, we're going to do everything by ourselves. We're going to write the software. We're going to develop all the hardware. We're going to design it." And what you're both talking about here is the automakers are backing off a little bit. They're saying, "Okay, we're only going down to this level on the development of the software. We're taking much more standardized components than we did in the past, and we're going to use those and apply them differently in parallel. They're going to be much more robust than what they were in most other applications, but it's still backing off from we have to develop everything ourselves and everything is customized."
I think, yes, you're right. So they want a standardized approach, but especially if you then look at the thing, so they want to develop standardized approach, but still want to really utilize the hardware. And I think here the key is also in all the software ecosystem and tools, you provide them that they really can develop on a high level, but still use the hardware features and yeah, really make use of the dedicated hardware which was built in order to get this high level of processing power which they still need. Because nowadays, if you define your car by software, obviously you also need some computational power, but it's always then in the domain, so it has to be robust. Your car should live longer than a smartphone. It also has a more harsh environment, so higher temperatures, and also passive cooling only, things like this. And also still or limited energy also comes on top. So you really need to enable this for them that they can develop abstracted from the hardware, but still make use of the hardware which is provided to them.
This slide is the model-based design support. So on the one hand, like you said, you need to enable specific hardware, but on the other hand, that specific hardware must be broad enough to support different applications and different models. So it's both DSP, neural network, very specific tasks, but also general computation. What you see here on this slide is the ability to go from a model, neural network model, for example, to the microcontroller hardware and be able to execute it from high level to right to the hardware. And that code has to be optimized, not just run. Because when you drive a car, you need to make sure that you're utilizing the hardware. You are very limited, right? So you want to make sure that everything is utilized and work fast. So all those things, all this automation and libraries that you can use and optimization of that flow, it's not only helping the software developer to generate code faster and safer, right? For functional safety reasons, for example, that is important, but also because it's structured and faster. The automation makes sure that you will use the right libraries that are already optimized in that flow. And you'll start from a neural network model. There will be a compiler that will take care of computation resources and will be able to utilize it and optimize it with the right libraries. and then it will run faster on that microcontroller, if it's the DSP inside, or the tri-core, the CPU, and all those components will talk together and be able to share tasks and schedule those tasks, and it's going to be a system running together in an optimal way.
Does that formal model also allow you to add in security? Because one of the big uses of formal going forward will be you can trace out any potential security flaws and paths.
Yeah, so it's both security and safety. It goes together. And of course, there are processes in place to ensure both functional safety and security. There are a lot of tests, manuals, documentations, and ways to make sure the compiler and the components here are safe when the software developer wants to use the tools. But of course, it is important to make sure that it's not just the compiler that is safe, but the entire system. So there need to be tests at system level as well.
In the past, one of the big concerns about when you're designing a chip is you were designing it primarily for a socket. It was pretty much standardized, and you really didn't know how a chip was going to be used. What's happening here is that you're moving much closer into the bigger system, which is the car or subsystem within a car, as opposed to just trying to create a chip is going to be a standard component. And now you really do understand, okay, here's how it's going to behave. Here's what we need to think about as we put this together. This opens the door for much more insight into the end markets. How does that change what's going on the design side?
From my point of view, it's also a challenge, what you just told, because especially in the past, it was with only a few dominant players in the market. It was really you build something which they want, and now you have to build a lot of system knowledge because you have many inputs from many different vendors. You don't want to build a chip for every vendor because this is simply not going to work. And therefore, you need to find out the market trends also on your own, because also still we are getting faster in developing hardware, but still with all the safety certification which we need to do definitely in the automotive market, it still takes a while, and therefore you need to be prepared for the future and really think in system where is the market going to, that you also can then serve what the end customer wants in 2 to 3 years down the line.
From a tools and software perspective, that require us to be flexible and modular in software components and support more and more applications and be able to accelerate them. We have to be aware of the trends. We have to make sure the improvements and future features that are coming are always meeting the requirements in the automotive market, whether it's performance, safety certifications, or other aspects that the end customers may need or may want to develop. We have to be flexible, and we have to follow the market closely.
Guy Ben-Haim and Kajetan Nürnberger, thanks for a really interesting discussion.
Thank you.
Pleasure.